Hello, folks. We're going to start again. We got quite a bit more to get through, hopefully. So let's pick up where we left off with how to partially specialize a function the right way. Right? Because remember from last time, function templates cannot be partially specialized. Right? You can't do it. If we have something that we want to behave like a function, which is to say it's a procedure for doing a thing from some inputs and getting some outputs, and we need it to be partially specialized on the type of those inputs, the right way to do it is to delegate the partial specialization work off to something that can be partially specialized, such as a class template. Right? Use the right tool for the job. If you need partial specialization, use something that can be partially specialized, and don't use something that can't. So in this case, I have a single function called isPointer, single function template called isPointer, and all it does is instantiate one of these two classes, one of these class templates. I have a primary template at top, and I have a partial specialization of this class. And this is a partial specialization because it's got angle brackets after the name isPointerImpl. It's got angle brackets. That means it's a partial specialization. And I just dispatch to one or the other of them, and there it works. And this is also how I could implement the isVoid trait earlier using a full specialization. Now you know everything there is to know about all these kinds of things, which is nice. But there's still one more thing that I want to explain. Let's talk about translation units. So here's a puzzle, which we're not actually going to puzzle over, but suppose we had to write a function to reverse the characters of a possibly multi-byte string in place. Only possibly multi-byte. We also want versions that work for ASCII. ASCII, UTF-8, different character sets, Latin 1. But we don't want to do it using the old, terrible MB, len, and MB, all those different functions with locales, how C did it. We would like it to be compile time and be able to parameterize it on the character set itself, and we're going to do that as a template parameter. So how I would use it might look something like this. I've got this function called reverse, and it takes as a template parameter, so it's function template. Keep calling these things functions. Takes a template parameter called charset, and that could be one of these little tag structs up here, struct ASCII or struct UTF-8, and depending on the value, or depending on the type that's passed in, I get one behavior or the other, right? Now reverse can be implemented basically like this. This is the, reverse each individual character and then reverse the entire string. Good interview question, by the way. Remember this for your whiteboards. It relies on mblen of charset, which is a function that's going to return, given where I am in the string, tell me how many bytes are in this next character. For ASCII, that's always going to be 1. For UTF-8, it could be anywhere from 1 to 4, or maybe 5. So we're going to need to define some full specializations of mblen here. Mblen of ASCII always returns 1. Mblen of UTF-8 returns something complicated that, I don't want to define all this in my header file. This makes me sad. I would like to move this definition of this template function, this full specialization, out into a CPP file, and another translation unit, term of art there. So I can do that. This is a definition, just like any other function definition. And I can make it a function declaration, just like any other function declaration, by just putting a semicolon there. And then off in my CPP file, I can write out the actual implementation of it, as we see here. So here I have my CPP file at the bottom, which has the definitions of my full specializations. And then in my header file, I have the declarations of those two specializations, and I have the definition of the primary template for reverse. Does that make sense? And this works fine. However, that's still a lot of code. I don't want all of that code. That wasn't that much. It was like that much. But still, I don't want it in my header file. I want to put my implementation code in my CPP file if I can. So how do I get rid of that? Well, that brings us to this next little bit of syntax here. So sorry, not quite yet, because first I can say, okay, well, I'll just specialize it. I'll specialize it fully for reverse of ASCII and reverse of UTF-8. I'll tell it that I have full specializations of these, and I'll put the full specializations down in the CPP file. But now I've repeated the implementation twice, and I don't want to do that either. So what do I do now? Okay. Well, now we get to a new piece of syntax here, explicit instantiation definition. This is a special syntax that means please instantiate this template with the given template parameters as if it were being used right here it doesn't tell you how to define it. It just says, I would like this defined, please. So it looks just like a full specialization, except that after the word template, where full specialization has empty angle brackets, I told you those were important because now they go away. Template without the empty angle brackets is a completely different thing, has no relation to an explicit specialization, and so it has a completely different name that could not possibly be confused with it, called explicit instantiation. And it looks like this. The word template with no angle brackets, and then you declare the thing again, basically as if you were going to use it. So like class vector of int, for example, is void v of void. And that just means instantiate the thing right here, please. Now, if I don't want to instantiate it right here, and I would just like to instantiate its declaration and say, well, it's defined somewhere else, I can just stick the word extern in front of it. Because that's what extern does, right? It's where it says, like, here's a declaration, the definition is somewhere else. And then you'd better define it somewhere else. All right, so that's an explicit instantiation definition and declaration. So there's one interesting thing about explicit instantiation for class templates, which is different from anything else. Because the weird thing about classes in C++, the neat thing about them in particular, is they can have members. A function cannot have members, a variable cannot have members, but a class can have members. And so when I explicitly instantiate the definition of a class, that counts as an explicit instantiation of all of that class's members as well. So when I say I'm instantiating class foo of int, I also get foo of int : f and foo of int : g in this translation unit as well. So this is a way, if you have a whole bunch of very similar templates and you would like to explicitly instantiate them all in one go, maybe stick them all as static members of some class and then just instantiate that class, boom. If that's a case you ever run into yourself, you know. So we can explicitly instantiate without specializing. It looks like this. So here we have the primary template still in the .h file. And we're saying extern template, no angle brackets. So that's an explicit instantiation declaration that says, I have explicitly instantiated this somewhere in my code. Not here, but don't worry about it. You know, just use it. Don't try to define it yourself. And in the CPP file, that's where I say template, no angle brackets. And that is an explicit instantiation definition that causes reverse of ASCII and reverse of UTF-8 to get instantiated there. Don't mix and match, though. These angle brackets are important. If I stick the angle brackets on up here, that says I have somewhere, not here because I don't have a body here, but somewhere I have an explicit specialization, a full specialization of reverse ASCII. But I don't actually make one in my CPP file. In my CPP file, I don't specialize it. I just instantiate the primary template because I forgot the angle brackets there. And so this is not guaranteed to work, although it does in practice for reasons of name mangling. Here's the deal with name mangling. This is exactly the case we just looked at, right? Right. So on the left, these are two translation units, the two little papery things, two different modules, two different CPP files that I'm compiling. And in the one CPP file, I've said template, bracket, bracket, int a, int. And that is saying somewhere in my code, I have a full specialization of a. Not here, but somewhere. And I try to call it. Across in the right-hand one, I instantiate the primary template. Now what happens that instantiating the primary template generates some code, and you know the code has a mangled function name. People name mangling, like vaguely familiar? Yeah, okay. So it happens that the name of the thing that gets instantiated there happens to mangle to the exact same thing as the thing that I'm calling, and so it will work. But try not to do that. And if you reverse it, and I put over here, this is an explicit instantiation declaration on the left without the angle brackets. And on the right, I've got a full specialization that says, well, here's the full specialization. We now have two competing definitions. I'm sorry, the thing on the left is not a declaration, it's a definition because I didn't say the word extern. So we actually have two competing definitions. And they're probably not the same, because the one on the left is an instantiation of the ... in the primary template on the left, and the one on the right has its own little ... that might have something completely different in it. And so the answer that I get from my main here is going to depend on whether it was inline from my translation unit or generated an out-of-line function called the other one, and it could depend on optimization level or what order they happen to get linked in, which order the linker decided to throw away the duplicate definition. So this is fragile even in practice and may change depending on things. So don't mix and match. Now you know everything there is to know about explicit instantiation. That actually concludes part 1. Awesome. Do we have any questions from the audience while I go to part 2? If you're lucky, you'll get an answer from the speaker while I go to part 2, which is a bigger, yeah.
So can you do explicit instantiation of classes and extern them as well?
Can I do explicit instantiation of classes and extern them as well? I believe that you can. Not 100% sure about that, but I think so, and I think that would do the obvious thing. Which is say, I have definitely explicitly instantiated this somewhere, but it's not here, and it would say that about all of the members of the class.
How do you explicitly instantiate a static member function of a template class that's also a template?
How do you explicitly instantiate a static member function of a class template where the static member function is actually a static member function template? Yes. And it depends whether that class template, are you making a template to stamp out instantiations of the static class? You've got 2 levels of cookie cutter there, right? And you can do each one individually. And this is what you'll see sometimes where you have like template class T, template class U, some stuff. That's the syntax for if I have a class template, which is a member, which is a template, and here I am making a cookie cutter to stamp out cookie cutters to stamp out the actual definition of the thing, because I have a template for a template of a thing. And I'm not actually going to cover that, which is too bad. All right, does anyone need a refresher on part 1? All right. So let's talk about some idioms that we can use with templates. Let's say I wanted to specialize on some condition that was more complicated than that, just make a full specialization for void example that I gave earlier. So here I have an example inspired from real life where I have a tree container and a vector container, and they both have iterators, right? I have a tree iterator that when I'm going through a tree, right, I can only like plus it. I can't like hop to n nodes ahead in the tree without just following the next pointers. But with a vector, I can just do a random access iterator. And I have a vector inset down at the bottom using them. Actually, okay, hang on. What is this, right? I said tree iterator, ampersand. I thought that whenever I referred to a class template, I always needed to put the angle brackets because otherwise it wouldn't be able to deduce what I meant. Well, there's a special case. The special case is if I'm actually inside the definition of that class template itself, then I can kind of deduce which T I mean, and T I mean is T. Right? I'm inside the definition where I've got my template parameters, like element. So tree iterator implicitly means tree iterator of element, because I happen to be inside the definition itself of tree iterator of element. This is known as I'm going to say it's an injected class name, and I'm probably pretty close to right. Yes, the bare template name can be used as a type name, in which case it's basically as if you put all the template parameters after an angle brackets. This is fine. It helps cut down on repetition, especially in declaring things like the copy assignment operator and things like that. I recommend that you use it. And especially that you know what it means when you see it. All right, so where were we? Right, so we have a standard algorithm called advance that takes an iterator of some type and advances it by n positions, and here's the implementation of it. It just calls n times. For random access iterators, we can actually do better. We could write something like this. Right? This is advanced specialized for vector iterators, where it takes a vector iterator of some element type. And in that case, it's just going to return begin n. However, no, wrong. That looks like it's supposed to trying to be a partial specialization, right? It's got the same name as this primary template, but it's like sort of more specialized, but it's not fully specialized. Well, function templates can be fully specialized, but they can't be partially specialized. No, don't. Therefore, we shouldn't do it this way. And we could do it the other way by implementing this class template. But let's just do something like this. Let's say for tree iterator, I'm going to generalize a little bit. I'm going to say we're not going to specialize just for vector iterator, because I might add some new kind of random access iterator later. So I've got my tree iterator, and I'm going to add a member to it because I control all these different iterator types, and I can just add a member that says supports plus false and supports plus true. And then I can make a function, a pair of function templates which are not, they don't look anything like partial specializations, because again, they can't be, because they take a different parameter type as the third parameter. One of them takes particularly false type, and the other one takes particularly true type. And I'm going to pass iter supports plus to those. Let me go back one slide. Let me point out for those of you who are already familiar with tag dispatch that for the sake of pedagogy in this case, supports plus is not a member type def. It is actually a member variable, a static member variable of false type. Have people seen true type and false type? This is one bit of type traits that is useful to know. They are, you might say, well, isn't that just bool? No, it's not bool. These are actually two different types, as different as int and double. They're very different types. And they happen to be, for some reason, associated with the semantic values of true and false. It's like as if we pretended that int were true and double were false. They're just two completely different types that happen to be associated with the concepts of true and false. And they're useful for things like this, where we're trying to overload on these concepts, these compile time concepts of true and false. And that's not using concepts in the Bjarne term. Yeah. I could, but that would make this slide a little bit more complicated. Does everyone see how this slide works before we go to the next one? All right. In practice, yes, it will look more like this. So up here, instead of declaring a static data member called supports plus, I will instead make a member alias, a member type def, named support plus. Supports plus, tree iterator of t : supports plus is now an alias for false type, and vector iterator of e : supports plus is now an alias for true type. And I do the same thing with advance impl here. And my advance calls this function advance impl with begin and n. And then this little expression here. Type name, iter supports plus, curly brace. And so the curly braces are there because we're trying now to create an object of that type, right? Those are the curly braces that you would, it could also be parens, that would also work. But why the word type name? How many people have been writing template code and you've had to stick the word type name somewhere? All right. How many people got like confused by that? All right, good. Well, so what's going on with this type name? So C++'s grammar is not context-free. Normally, context-free grammar is one of these CS something terms that you don't really need to know. But in order to parse function definition, you actually need to know something about the context in which that function is being defined. Namely, you need to know things like, in this example, is A function or a type? If A is a function, then A of x is a function call. If it's a type, then this is like int x, right? If A is a type, I'm just declaring x to be of type A. So I need to know something about the context. What is A? And so if the context ends up being dependent on a template parameter, where I don't know what that parameter is yet, t : A, I don't know what that is. That might be a function, it might be a type, it might be something else. Right? So how can this possibly work? How can I have this function here, function template, and I instantiate it with S1, where A is a function, then this should be a function call to S1 of A, S1 : A. And in this case, foo of S2, well, this should be a declaration of an int. How can we possibly make this work? The answer is we can't. That's too much work. So we're just going to assume that any name that depends on a template parameter refers to a non-type, non-template, plain old entity. It's going to be a variable or a function, or but it's a noun. Well, type is a noun too, but it's not a type. It's not going to be a type or a template or any weird thing. It's going to be a regular old, the normalest thing you can imagine. So in this example, foo of S2, if we try to compile that, it's going to go instantiate it, and it's going to say S2 : A is some plain old thing that I'm going to call with X. Oh, but it's not a plain old thing, it's int. Well, that doesn't make sense. It's going to give you an error. It's going to say it was parsed as a nontype. I assumed it was a nontype originally. But instantiation of foo of S2 yields a type, so hard error. And this is how we fix it. We stick the word type name in front. So to let the compiler know when it parses that template, hey, this thing coming up, it might look like a regular old plain thing. You're going to assume it's a plain old thing because it's dependent on a template parameter. But it's not. I'm telling you it's a type name. So please treat it as a type name. That means this is a definition, variable definition. And now if I try to compile this one with S1, it will say, hey, you told me T: A was a type name, and it's not. So there'll be an error. Similarly, we have things to refer to a template. Let's say I had these three, S1, S2, S3. And I try to do this. Does this work? Give you a moment to digest this a little bit. S1 : A is an int with value 0. 0 less than 0, greater than X. Discard the result. Okay, sure, that works great. Foo of S2. T : so S2 : Now, at this point, A is not a plain old thing. A is a template, so we have to tell it template A. Right? Template A, okay, this is an angle bracket, and this 0 is substituting in for n, so n equals 0 in that instantiation. And then we're going to call it with X. Okay, so that works. And then in S3, we actually have a variable declaration. We're declaring variable X to be of type S3 : A with n equals 0. Okay? So that's where these type name and template keywords come into play. So hopefully from that you can figure out where to use them in future. Questions about template, type name, dependent contexts? All right. So let's go back to a tag dispatch example. We see now why we have the type name down there, because if we didn't, it would assume, because iter is a template parameter, iter : supports plus is probably a variable. And that's why my original example where it was a variable worked out great. As soon as I make it a type name instead, well, now I need to tell it explicitly when it parses this template, hey, this is a type name coming up. Otherwise, I get a syntax error. Okay, so now you know everything there is to know about tag dispatch, except what if we don't control iter, right? Because this entire thing up here depended on my being able to insert this supports plus member into tree iterator and vector iterator. What if I wanted to work with plain old pointers? Okay, we have nose class off of which to hang our supports plus member type diff. What do? We make one up. So I'm going to make up a new class. I'm going to call it iter traits, and I'm going to have it's going to be a class template, and the primary template is going to say by default supports plus is an alias for false type. And for vector iterator, supports plus is going to be an alias for true type. This is a partial specialization, which is totally fine because class templates are allowed to do partial specialization. And I'm going to make another partial specialization for t-stars, where supports plus is also true type. And then I can just use type name iter traits of iter, : supports plus. If iter happens to be one of those types for which we've partially specialized the iter traits class template, supports plus will be true type. I will make a new variable of type true type. I will pass that as the third argument to advance impl. Function overloading will say, you must want the one that takes the third argument of type true type, and it will do the fast random access implementation. If it's not one of those, it will instantiate the primary template, create a variable of type false type, pass that to the one whose third argument is false type. Yeah. Cool. SDL best practices. You can also, if you want, you can take this iter traits of iter supports plus, and the fact that we had to write type name in front of it, you can again get rid of that by creating a alias template and stick the type name up in the alias template. And then your code gets cleaner because an alias template always refers to a type, so we don't have to stick type name in front of it anymore.
Just a question on tag dispatch. It looks like it comes with some additional stack pressure because you're hitting one more argument on the stack and it's internal
assumption that the compiler can get rid of that for you, or are there other methods for high performance?
Yes, so the tag dispatch, we have one more nested function call in here, is the assumption that we can just inline it away. Yep, sure is. Yeah, compilers are great at inlining. And now you know everything there is to know about traits classes. Cool, so let's talk about declarations and definitions. We have three cases here. One is normal entities like functions and variables. This is the case that we should all be real familiar with. This is the case that exists in C. So, you know, I have here a function declaration, a variable declaration. In the other translation unit, right? Two different translation units here, two different CPP files. I have the definitions, and when I try to use them from the left-hand translation unit, well, they're declared, so it compiles fine, and then the linker finds the definitions over in the right-hand side, and it links, and we're happy. Inline functions and variables work a little bit differently. You can define them in two places, and it will work just fine. And the way that works is that the linker will find out that, oh, you have two definitions of this, and where normally that would be a multiple definition error, the linker will instead just throw away all but one of them. Just quietly throw them away and take whichever one happened to come in first or whatever heuristic it wants to use. So in this case, I've actually defined A in two places, and this works just fine. And I'm actually using it in two places as well. Yes? What if they're different definitions? Then you have undefined behavior. So don't do that, yeah. Now suppose I do something like this, where I have a declaration of the inline function over here, but I haven't told the compiler how to define it, but I'm still trying to use it. And then over on the right-hand side, I have something that does create a definition of it. So if I manage to get this all the way through the compiler to the linker, which I believe you can in all major implementations with at most like a warning, it will actually work because the linker is totally happy. It says, oh, you're using A, I've got a definition for A, and it links. But this is officially ill-formed, so avoid this. However, the linker will kind of do the right thing. However, this is ill-formed because an inline function or variable shall be defined in every translation unit in which it is ODR used outside of a discarded statement. And in the left-hand translation unit, we have an inline function or variable which is ODR used in main, but it is not defined. It's defined in a different translation unit in the same program, which is why the linker is totally happy and it probably works in practice. But yeah, officially don't do this. And especially, I mean, a good reason not to do this in practice either is, let's say that someone does some refactoring on the right-hand side and they remove foobar. Or let's say they turn on optimizations on the right-hand side and A gets inlined, so there's no longer a definition. So at this point, there is no definition of A on the right-hand side because we didn't need it. So, you know, we got rid of it at compile time, and we go to link, and suddenly there is no more, and now we have an error. So it's always good to make sure when you use an inline function, make sure that you also provide the definition of it, because I mean that's the whole point of inline, right? We want to inline the definition into the call site. So it'd be nice to tell it what the definition is. So templates work under very, very similar rules. Here I'm using a particular specialization of A, let's see. By the way, I've been color coding these in a little way. I've been underlining where the thing is needed, and bluing where the thing is actually defined. So here it's needed and defined in the same place, and over in the foobar it's needed and defined in the same place, and it all works great. Again, we have two definitions, and again, the linker does its magic thing that does for inline, which is throw away all but one of them. By the way, the buzzwords to remember there are link once section, if you are on GCC or Clang or a Unix C type operating system, or for Windows, comdat sections is how that's actually implemented. You throw away all but one of them. Or we could do something like this. On the left-hand side, I'm trying to use a sub int, but I haven't told you how to define it. So it's not going to get defined over there. But it will get defined on the right-hand side because I have explicitly instantiated it. And so I'm using the explicit instantiation. I'm defining the explicit instantiation. This should work. In this case, I am using an implicit instantiation a sub int on the right-hand side. So it will get defined over there. It's needed on the left-hand side. The linker will probably link them together, and it will just work. However, we have the same issues here as we had with the inline case. What if someone refactors away foobar? Then my code breaks. What if a sub int actually got inlined, and then the compiler decided it didn't need to generate an out-of-line definition of it? Then my code breaks. So while this will work at 0, you start turning up the optimization level and suddenly it breaks. It may be because you are using a template instantiation in a place where you have a declaration for it, but you haven't defined it. And so the compiler just generates the call, and then eventually it breaks in the linker. Right, here's the example here. A-int is unused. Then, of course, we have a linker error. There are at least 4 ways template stuff can go wrong. We're going to talk about some of them now. When is instantiation needed? So a decent rule of thumb is never instantiate anything you don't 100% have to. And this is the decent rule of thumb for understanding the compiler's point of view. When the compiler sees something like this, I have a template here, and it has a static assert inside it that says size of t is 2. And I'm trying to instantiate this class with int. Now, size of int is not 2. Size of int is 4 for most people. I'm going to assume that it is for these slides. So I try to instantiate, and it works. I can actually create a pointer to a c of int just fine. The static assert does not fire. And the reason the static assert doesn't fire is that it doesn't need to be instantiated. That's in the body of the class. That's in the definition of the class. And in order to get a pointer to it, I don't need to have a definition of the class. I don't need to know its members. I don't need to know how big it is. All I need to know is how big is a pointer to it, and the answer is how big is a pointer on your system. And I just need to know that it is a class, which it is. So this is totally fine. Now, if I actually, if I actually were to create something without the pointer there, now suddenly I need to know how big is the class. And that means I need to know what are its members. But let's first, quick sidebar on static assert. Static assert false. How many people know static assert like pretty well inside out? Yeah, cool. All right. So static assert is a compile time way of making your program ill-formed and requiring a diagnostic. This is nice if you are a library writer and your user is doing something stupid that you want to stop them from doing. You can just stick a static assert in there to say, hey, you're probably doing it wrong. Or it's a sort of unit test at compile time. So if you are particularly relying on some invariant and you really want to check it, like size of int equals 4, like I know my code's going to break if we go to a platform with 2-byte ints. I'm just going to static assert it right here, and that way my code will fail to compile because, again, the program will be ill-formed if that ever breaks. Static assert false always makes the program ill-formed. If it's some constant expression evaluating to false, and it doesn't depend on any template parameter, you'll have a real hard time getting that past the compiler, because the compiler will just be going along, even parsing through a template, even if you don't instantiate it, and it'll say, you know what? In this example, F won't even compile. Doesn't matter if I instantiate it or not. I'm static asserting inside it that size of int is 0. Well, that can't possibly be true. And so the compiler will actually reject that out of hand and just say, no, F will never compile. This is dumb. You should just delete all of this code. And that may sometimes not be what you want. If you run into this situation where you're trying to static assert false somewhere and it's not letting you because it knows false is always false, the pro tip there is make it depend on a template parameter. Something like this where I say static assert size of t for this template parameter is 0. Well, that's still never really true, barring compiler extensions, because Nontype has size 0. But because it's dependent on t, the compiler will actually wait until it knows what t is to substitute it in and find out. So what I have here is a function g that if you use it, it'll static assert. And if you don't use it, it won't. And again, by use, I mean something that actually requires the definition to get instantiated. Does that make sense on static assert? Because this is useful. All right. So here's an example where I'm instantiating the definition of the class. And if you look closely, you'll see that each of the lines here, SDM, SMF, and F, has a definition that also shouldn't compile. Right? In 2 of the cases, I'm static asserting that size of int is 2, but of course it's template dependent, so it's okay. In the other case, I'm trying to take nullputter and cast it to a t, which is int. And that shouldn't compile either, because you can't cast nullputter to int. But I can still create an object of type C, because here, I don't need to know the definitions of SDM, SMF, and F. All I need to know is their declarations. I need to know the definition of the class, and therefore I need to know the declarations of all its members to find out like which ones take up space and so on. But I don't need to know what they're initialized to. So again, the compiler is applying its rule of thumb, which is never instantiate anything. You don't absolutely 100% have to instantiate. I'm going to skip a few of these slides. Remember, the template definitions behave basically like they have the inline keyword attached to them. So in this case, we covered this actually a little bit earlier with the two sides and which things you could get away with in practice and which things you can't. In this case, you can get away with FF1 in practice, even though you shouldn't do it, because FF1 might be defined somewhere else. The compiler will often let you off with a warning, and as long as the linker is happy, you're happy. In case FF2, we will actually try to instantiate the body of FF2, of this inline function, and we will find out that the static assert fails. In fact, we'll find it out very quickly. So when I try to do FF2, when I try to even define FF2, it won't work. When I templatize these, with FF1, that's totally fine, but it better be defined elsewhere. With FF2, now I'm trying to call the thing, so I better try to define its body, and I find out that the definition of its body contains static assert of something which is false, and therefore a static assert fails. If I add an explicit instantiation definition, remember explicit instantiation definitions? We have extern template that says, I promise that someone somewhere else has explicitly instantiated this, so you don't have to. The compiler will say, oh, I don't 100% have to instantiate this? Cool, I won't. And it will completely ignore that static assert and it won't fire. It probably fires in the other translation unit if you did it right, but it doesn't fire in yours. Or if I fully specialize FF3 and I say, somewhere else, not here, but somewhere else, I have made an explicit full specialization of FF3, of int. So you don't have to instantiate the primary template. Please, in fact, please don't instantiate the primary template. I want the full specialization from elsewhere. And it says, okay, I don't care what's in the primary template anymore. So this is also fine. Variable templates work very similarly to function templates and class templates. But watch out, I have found that Clang and GCC currently disagree as to what constitutes a definition of a variable template. So in GCC and MSVC, when I just say template type name t int vt, they say, oh, yeah, that's just as if I wrote int vt, semicolon. It's a definition, right? It's a global variable, it's a definition. It reserves space and so on. For Clang, for some reason, this is just a declaration. I don't really understand it. It's as if you put the extern keyword in front of it. If you wanted it to be a definition, you would need to actually initialize it. You'd say equals 0 or empty curly braces or something. And then it would say, okay, this is now a definition for sure. I feel like this is a bug in Clang, but I don't really know. All right, now you know everything there is to know about implicit instantiation. I know that went like super fast and was probably confusing. But we're going to have less confusing stuff coming. So let's all forget that that section happened. So hopefully by now everyone's seen variadic templates, so I'm going to skip over the motivation. And let's talk about variadic template parameter deduction. Yeah, all right. So template parameter deduction, in a nutshell, we already covered all of it except for variadic templates, which I said we'd get to in part 2, so here it is. What happens in this case? Here I have a template, it's called f, and it has a certain number of parameters. One of them is named t, and the others are named u's. It has some parameters, collectively named u's, which are of type capital U's. And so they all contribute to deduction, right? The parameters u's contribute to the deduction of template parameters u's. So what am I telling it? Well, I'm telling it explicitly through the angle brackets that the first template parameter, which would be t, is char. Okay, I know that t is fixed as char. Then I'm going to deduce what u's are. So it looks like the first one of u's is int, and the second one is int, and the third one is int, and then we're done. Okay, cool. That's the simple case. Let's try this. Now I'm telling it, well, the first template parameter, t, that's char. T is fixed as char. And now the second template parameter. This is interesting. The second template parameter is the first of the u's That's also char, but I'm not saying anything about the other u's. Okay? So then we go and we look at the arguments. Well, the first argument, that's the first one of the lowercase u's. That doesn't contribute to deduction because we know that the type of that is char, right? And then the next one, that's an int, so we deduce the second one of u's as int, and the third one is int, and then we're done. Okay, we get that. Does that make sense? Two hands, yeah.
So in the first line, if the 0 was in single quotes, would use be int?
If the 0 is in single quotes on which line?
The first line for f char. And the 0 was in single quotes, so it was a char. Would your use just be int?
My use would be char int int.
But t is char.
Yeah, t is char.
And there's 3 arguments.
But the 3 arguments all contribute to use. T is actually not deducible here. If I don't specify t, it won't compile at all.
Okay.
Also question? Yeah, okay.
The u's don't have to all be the same type.
The u's do not all have to be the same type. They all have to, just like when I pass multiple ints to a function as function parameters, the ints don't all have to have the same value. Here, when I have multiple types as template parameters, they don't all have to be the same type.
You just like instantly go and specify like templates then? So if you did char, comma char, and then like in the brackets and then have your params, would that just specify like the first 3 of chars then?
Yes. Yes, you can just keep going as long as you want there in the angle brackets, or outside them for that matter. So as far as explicitly specified template parameters are concerned, the first pack expansion encountered in the template parameter list basically just soaks up all of the remaining explicitly specified template parameters. Those are the things in the angle brackets. The type deduction step might wind up lengthening that first pack, but it will never shorten it, right? Where we said, like, well, I know that the first element of use is char, and the second element is int, and the third element is double, but I don't care what happens after that. Well, we might go on and we say, oh, well, I can deduce that the fourth one is int, and the fifth one is whatever. Yeah. So let's look at some of these cases. In this case, we are specifying explicitly that t is int, and use begins with char, int, something, something, something. Well, v, we don't know anything about v. Now, you might say, well, I can look at this and I can predict that v would be int, and then use must just be the single element char. But that's working right to left, and that's not what the compiler does, and that's not what the standard says the compiler should do. The compiler is doing its job in this case. It's saying, okay, t is int, use is char, int, maybe some other stuff, and v can't be deduced at all. And because v can't be deduced at all, this will refuse to compile, right? Because it doesn't know what v is. In the second case, t's starts out with int and char, and then, well, that's all we know about that from the template parameter list in the angle brackets. So then we go and we look and we say, we have one function parameter, and it's a double, so u must be double. And then we're done. And we have completely deduced everything there is to say about this function, and so it works. In this case, let's see, we start off with int, char. So t starts off as int, then char. So the first 2 parameters don't contribute to type deduction at all, so it's okay that the second one isn't a char, it's an int, but it will get converted. And then there's a double, so we add that onto the pack. So t's is just int char double, and that also works. This is actually a little bit interesting, right? Because you might say, well, I said h of int char, and I'm giving it 3 arguments. Why doesn't it tell me I just have too many arguments? And the answer is, well, that's not how variadic type deduction works. Questions about this slide?
Why can't t or v be reduced? Could there be a case where like int is t and char is u and int is v?
Yeah, you would think so, but no. Why can't v be deduced? Well, because the use is the first pack expansion that we encountered, and it soaks up all the rest. So use is char and int and maybe some other stuff, and then there's nothing left for v, and it can't be deduced from the parameter list. So.
But then why does the second one work?
Why does the second one work, given that the first one failed? Because in that case, we can deduce u from the parameter list. The parameter list tells us that u must be double.
In that second example, if you expanded the types out in G there, would it always be the case that whatever the parameter you put in as the actual argument would be attached to u?
I'm not sure what you mean by expanded out the types.
So if I said G int, comma char, comma double,
Then t's would be int char double, and U would be derived, and it would probably complain about the number of parameters that you passed. Well, in that case, it would be fine. But yeah, there's no way to specify. In the second case, in G, there's no way to tell it explicitly what U is. U can only ever be deduced from the parameter list, because anything I throw inside those angle brackets is just going to keep getting added to T's. There's no way to specify U in the angle brackets. Anything I throw in there is going to get soaked up. Does that answer the question?
And likewise, if you had like another, in the actual template definition up there, if you had another class after U, then it would take, if you had a second parameter, that's what would be added there.
I believe yes, but I'm going to move on to the next bit. So as far as deduction is concerned, right? So we talked about explicitly specified template parameters. Now let's talk about the parameter deduction. A parameter pack contributes to deduction only if it comes at the very end of the parameter list. Otherwise, it does not contribute to deduction. So in this case, I have in this case I have an F, and I'm not going to specify anything about the angle brackets. I'm just going to rely on the deduction. And I'm going to deduce that the first parameter is U, so that's a char, U is a char, and then the rest of the parameters, int, those must be the T's, so it deduces just fine. In the second case, the U's, these parameters, all of these parameters don't contribute to deduction. And I have a T at the end, but that doesn't work either. Like there's just nothing I can say at this point. I'm like, well, x1, 2, some of these x1, 2 things are probably some of the U's, but the U's aren't contributing to deduction, so I can't say anything about capital U's from this. And so yeah, I just don't know where to start with this one. And with case H, here I am explicitly stating that T is int and that U starts with int. Now here the U's don't contribute to deduction, but we know they start with int. So let's say, okay, this one, well, it's a char, but we said it was int, so it's int. And this is int. And then we've run out of the U's that were explicitly specified. So this next thing must be a T. So T must be int. And we have fact explicit, well, sorry, actually, that T doesn't contribute to deduction either. We already specified that one too. So this just happens to work. It's not a very satisfying answer when I say it like that. So the trick here is that the parameter pack contributes to deduction only if it comes to the very end of the parameter list. So only in F do we deduce anything about T's. In the other cases, we're not deducing anything about U's. Yeah?
Can you confirm or deny that you can't have two parameter packs as template arguments?
Can I have two parameter packs as template arguments like this? So the trick is, what does it mean to contribute to deduction? Again, GCC and Clang differ on this, and MSVC tends to agree with GCC. In this case, I'm saying explicitly that T's must start, the first one of T's must be int, the second one must be int, and I'm not saying anything about the others. However, T's do not contribute to deduction. So Clang says, well, you said T's couldn't contribute to deduction, that's the very first thing in here, like I don't know where to start. All right, you get a compiler error, hard error. MSVC and GCC both say, oh, well, you told me it was int, and I'm not sure what comes later, but okay. So this is an int, that's an int, and then this next thing must be U's, and so the first U must be an int, and then I run out of parameters, so okay, so U's is int, or that's a typo there for int, I think these were original, that was a 3.0. If that was a 3.0, this would be double. So yeah, so again, there's some confusion in the compiler world about what contribute to deduction really means. Now you know everything there is to know about template type deduction, even for variadics, and I think that's the last everything you need to know about template type deduction. Yeah?
Yeah, so what would happen if we don't specify any type for F?
What would happen if we just said F parens 1, 2, 3? In that case, I believe that Clang gives you a compiler error, and MSVC and GCC say, well, you didn't tell me anything about T's, so I'm going to assume it's empty, and U's is int. And it doesn't make a whole lot of sense, but this code doesn't make a whole lot of sense. Don't do this. All right, let's take a quick break with some patterns. How many minutes do I have left, by the way? All right. Well, let's try to real quick do this. So the CRTP is a useful pattern to know. And in fact, it's so useful that you can come see me afterward because I want to talk more about C++ 11 and I want to talk about these things. So I hope you all do too. I hope we're all very excited for C++ 11. Because here's some things that are going to be new in it. One of them I already mentioned, inline variables. In fact, Bjarne mentioned it. He said don't use them because they're global variables and they're terrible. I think if you're going to use global variables, make sure they're inline. Yeah.
On that, can we make static inline variables?
Can you make static inline variables? I believe that you can.
When I say static, I mean for class static, not static in static.
Oh, static data members that are inline.
Static,
Yes, definitely yes. Definitely yes to that one. And that's pretty much all I have to say about inline variables. Let's talk about template auto. This is a neat thing, but it's not really that neat. I haven't talked much about template non-type parameters, but by now when you've seen all of the ways that you can kind of match up and deduce things, you can figure how a non-type parameter would work if such a thing existed, which it does. For example, here, there's a very common one whenever you use a std array, right? I say std array of int, comma, 10. That 10, still in the angle brackets, is a non-type parameter. So in that case, t is explicitly specified as int, and the n parameter is explicitly specified as 10. You can also deduce template non-type parameters. And you can see that when you take there's a function called size that takes a reference to an array of n elements, and you can actually deduce what the n is in most cases. However, mostly when you have these template non-type parameters, you will see them mostly in metaprogramming contexts. Like you can create these index sequences of integers like that. And you also very frequently end up with things like integral constant. Actually, true type and false type are special cases of integral constant, happen to be associated with true and false. So I can do things like this. And template auto, when that starts coming and you start getting scared by that, know that that is basically just collapsing something like the above into that. So instead of now having two parameters, one to say what is the type of the thing that's coming next, and the other one to say what is the thing, we can now just have one parameter, and we no longer really care about what its type is. We can get it with decal type if we want it. But as with generic lambdas, we just say auto, and we just get the thing. Also, remember when I said in part 1 that class templates can't do deduction? There's a thing coming in C++ 17 that Bjarne alluded to. This is the slide from before, and remember when I said that we can't do deduction on class templates? Coming in 17, a way to do deduction on class templates, at least for the constructors thereof. And the way this is going to work is we're basically, whenever we see something like this where there's a bare template name for a class template, and it's not followed by any angle brackets, then we know when we're constructing an object of this type, we're going to pretend that we have a make helper function, like make pair or make tuple. We're going to pretend that that exists, and it has the exact same signature as the constructor of the primary template. So in this case, we have a make myvec that takes a t. And we're going to pretend that instead of calling the constructor of myvec something which we don't know yet we're trying to deduce, we're going to pretend that we called make myvec of those exact same arguments. And then we're going to do overload resolution on that, and we're going to do template type deduction and so on, and we're going to deduce that, if I called make myvec of 1, then t there would be int. So I'm going to say t here is int. And I'm just going to assume that you want a myvec of int. And this happens to work really great for pair and tuple. Here's a more complicated example. If I have two different constructors for myvec, it still works. I'm making a myvec. I resolve make myvec of 1. In this case, overload resolution looks at these. Now, these are not partial. This is not a partial specialization. Functions can't be partially specialized. We have two different functions in the overload set, but this one is more specialized than the other. So this is a better match. Oh, I'm sorry. Nope. In this case, 1 is not a pointer. Sorry, 1 is not a pointer. So we do this one. Make myvec with t equals int, and we get a myvec of int. So it does right. In this case, we have an address of an int. So in this case, this one is more specialized. So we take this one with t equals int, and we get myvec of int using the pointer parameter. So this is a case where we have deduced something for t that is not the thing we passed it. We passed it an int star, but because there's this extra constructor that takes a t star, we can deduce t equals n. Does this make sense? This is the first non-totally obvious example of how this might work.
It has to have make underscore in the template name, so that the compiler itself is actually paying attention to the naming of.
The naming of this make myvec, this is a completely fictitious function. It does not exist in your code. The compiler is kind of pretending that this make function exists based on the fact that these constructors exist, and then it's also pretending that you called it. You don't actually call it. Make pair and make tuple, well, they will still exist for backward compatibility, but you will not continue to make helpers.
Does this interoperate with auto, so I can say auto v equals myvec left parent int %i?
Yes, it does. It does interact with auto, almost always auto syntax as well. Myvec of 1 or myvec of address I would also work. Here's another example. We now have a template myvec where it has one overload that takes a t and one overload that takes a double. So let's pretend that we had these two function templates, and we're calling it with a double. Well, it turns out that we're trying to call make myvec of 1.0, but the second overload, this one, which takes a double, we'd love to call this, but we don't know what t is. T can't be deduced, so it doesn't participate. So we go to this one and we say, now t is double. Okay, I know about that. And we make a myvec of double. Or in this case, where I have a partial specialization of a class template, in this case, it's super unclear. I think not only will the compilers disagree once this is implemented, but I think the standard needs a little bit of love in this instance. But in this case, it sure looks like we would get a compiler error because we're going to deduce that t is int star, and we're going to see that there's a partial specialization for int star, and we're going to try to call that constructor, and it doesn't exist, and we're going to have issues. So there's a little bit of work to be done on the specification yet. This will also mean that there will be a difference between these two classes, where right now there is not. The difference here is in the first case, I have a myvec that takes a t, and in the second case, I have a myvec that takes some type def for t, some member type def for t. And if I were to actually construct the overload resolution here, and I would try to call the red one, it would work great. T would be int. In this case, I know that myvec of t : iter : type is int. What does that say about t? Well, I don't know, because I'm back in the same problem I was in C++ 14 of, well, I know that some crazy member, I know something about t. I know maybe its size, or I know that some member of this particular template is int. That doesn't tell me what t is specifically. So in the blue case, I wouldn't be able to use the new feature. In the red case, I am able to use the new feature. And if you want to guide deduction to get it to do the right thing, there's a syntax for that. It looks a little odd. It doesn't really look like a declaration, but that's also because it's not really a declaration, because these constructors exist already. You don't need to redeclare them. But you need to in some way guide to say, when someone does something that looks like a myvec of double and they don't say anything about which myvec they want, they probably want myvec of int. And you do that with this exact syntax with a little arrow. That's a deduction guide. And they participate. And the third one is clearly the best one, so on and so on. You know all the crazy stuff coming in C++ 17. And now we're actually done ahead of time with 2 minutes remaining or something. If anyone has any questions, I can also go back and talk about mix-ins. Question?
So you were talking about parameter packs before. Let's say you had foo
why did it deduce to int, comma, int, comma, int instead of int as r value, int r value, int r value?
Because taking the why when I have foo of 1, 2, 3 does it deduce int rather than intref, comma, intref, comma, intref? Because int works, and we don't like adding multiple ampersands unless we need to. In fact, we never like adding multiple ampersands, and we only add one if we really, really need to. That was from part 1. I don't know. Were you here for the first part? Oh. Okay. Well, the same rule applies as in part 1. All right. Well, that's it. Thank you all for coming.